So we've seen these things before that we're about to take a look at, and it's basically a kind of comparisons. And I'm going to just kind of go through the kinds of comparisons that we've either encountered or we're going to look at today. And there's two that we're going to look at. I just want to kind of go through some basic comparisons. And the first one is what we call a fraction. And a fraction is a part divided by a whole. And that's basically what it is. Like if you have slices of pizza, you can think of it like you have 8 slices of pizza and 5 of them were eaten. So what's the fraction of pizza that was eaten? Well, the 5 pieces that were eaten divided by the 8 original pieces, or 5 over 8. The next thing is called a rate. And a rate compares two different, you could call them subjects, or two different substances, or two different kinds of things. We can get kind of vague on this. We'll look at it. An example of a rate is when you look at speed. You're comparing distance with time. So I'm going to call them subjects. So let's do that. So subject 1. Subject 2. And these could be wildly different. You could have, again, distance and time. You could have dollars and pounds. For say you're buying meats, for example, how much per pound. Finally, the other one is called a ratio. And when we talk about ratios, we're actually talking about the same subject or the same substance, just different versions of it. So we have a subject, version 1, and a subject, version 2. Now this might seem kind of strange. We're going to talk about rates and ratios today. Again, rates could be two vastly different things, like money and pounds, distance and time. But with a ratio, we're going to actually talk about the same kind of subject. They just have kind of different versions of it. A good example of ratios are games. Like let's say you're playing basketball games. You have the comparison of the number of games won. So the subject is games, and version would be wins. And then you could have the subject is still games, but now we're looking at the version of games lost. So that's the idea of ratio. We're going to revisit this later. But these are sort of the 3 common comparisons that we deal with. Fractions, which is part over whole. Rates, which is one subject compared to another. And again, they could be vastly different subjects. And then ratios, a version of a subject and a second version of that same subject. Games you've won and games you've lost. But we're still comparing games. So that's going to be the goal today. We're going to explore these 2 things. And there's one other thing we're going to look at called proportion, which is a type of equation, but we're usually going to be comparing usually ratios, or an equation with ratios. So first off, we're going to take a look at rates. And rates compare two different things. So for example, let's say you drive 100 miles in, say, 50 minutes. To be doing something like that, let's say you're on a racetrack or something. You go to some racetrack, say sort of a local racetrack, you've got your car, you've been working on the engine, and you just want to see what you can do with it. So you do your laps and everything. You do 100 miles in 50 minutes. So the way we describe this is we're going to compare distance and time. So we can think of these as our two subjects. The first subject is distance, and the second subject is time. And so to come up with our rate, well, that's it. We just take 100 miles and we place that over 50 minutes. And so this would be our rate. Now, what we typically do with rates is we like to work with something called a unit rate. And a unit rate is when we reduce our rate so the denominator is 1. I'm going to be careful. I'm just going to say bottom number, just for now. I'm just going to say bottom number. I want to be careful with that. So these denominator and numerator typically have meanings that are very much tied to fractions. So I'm just going to be careful. I'm just going to call it bottom number for now. So the way we can do this we want this, instead of being 50 minutes, we want to make it in the 1 minute. So what we can do is divide by 50. We're still going to follow the rules with fractions. When we multiply or divide on the bottom, we're going to multiply or divide by the same amount on top. So 50 divided by 50 is 1. And we haven't done anything to the minutes, so we're just going to leave it there. 100 divided by 50 is 2. And we haven't done anything to miles, so miles just stays there. So the unit rate, the version of this that's a unit rate, will be 2 miles per 1 minute. And we like to express rates in terms of unit rates. You've heard of 50 miles per hour. Well, that means 50 miles per 1 hour. So in this case, we can call this 2 miles per minute. Questions about that? So let me see, let me pick out something from the homework. So let's say you have this. Let's say you do this. Well, let's say you type 544 words in 8 minutes, and you want to find the unit rate. So we have 554 words for every 8 minutes. So typically, this isn't always the case. We typically put the subject that's not time on top, and then the second subject, if it's time, on bottom. That's not always the case, though, but it's a very common thing to do. So you see miles per hour, meters per 1 second, these kinds of things. So we can start out with 544 words for 8 minutes. Now we want the bottom number to become 1. So that means we're going to divide by 8. Well, 8 divided by 8 is 1. And then 544 is 68. .544, if you divide it by 8, will be 68. So we have 68 words per minute, or 68 words per minute written like this. Some questions about that? All right. So let's say you have something like this. I'm not sure what the price for bananas is, but let's say you can do this. So let's say you get 4 pounds of bananas for 68 cents. Find the price per pound. So we want to find the price per pound. So they kind of give us a clue. Price per pound. That per kind of acts like the fraction bar. So this is going to be on top. This is going to be on bottom. So let's start out with what we know. We do have a price. It's 68 cents. And we don't have per pound, we have 4 pounds. That's the best we can do. Let me go with 4 pounds. So given what we've been given, we take that. We can't get a price per 1 pound, but we do have a price per 4 pounds. But we can convert this to be per 1 pound. And that means dividing bottom and top by 4. So like 1 pound. Let's see, 68 divided by 4. Is that going to be? Will be 17 cents per 1 pound. Or $0.17 per pound. And so that's going to be our answer. Questions about that? All right. So unit rates are very popular, and I think one of the reasons this is done, it's easier to visualize. When you're asking, like, say, I can get 17 pounds for $3.78. It's like, well, okay, 17 pounds. Well, what's the price per pound? Because that's going to help if you're say you're doing like a recipe or something. You're cooking a large dinner, and you need to estimate. Well, the recipe calls for 3 pounds. This is 17 pounds for $3.78. So what would it be per pound? So I can figure out how much this is going to cost me if I'm only buying 3 pounds. So, that's kind of the idea. It's maybe a little more. Excuse me. It's a little more user-friendly because we might think in terms of the pounds, the number of pounds that we're working with. And if you start with price per single pound, it's easy just to multiply that, and then you'll have what the price will be for you. So anyway, that's the idea. It's a little more user-friendly. And sometimes it's easier to visualize too. So that's the idea of rates. Let's do ratios. Again, with ratios, what we're comparing, it's 2 different versions of the same subject. So 2 versions of the same subject. So let me give you an example. So let's say we have this. You're on a basketball team and you played an 11-game season. It could be sort of like an organized neighborhood team. It could be something organized through work. There's a local basketball league. You join the team and you have this season. And in this season, your team wins 7 times and loses 4. So you're 7-4. So the subject in this case it's games. And then we have 2 versions. Abbreviate version VER, period. So the first version wins. The second version, losses. So we're going to stay in the subject of basketball games. We're going to have versions where we win and versions where we lose. So if we talk about the ratio of wins to losses, Now, a key thing here, we talk about ratios. The first version, that's what goes on top. Second version is going to be, or the second one's going to be what goes on bottom. So first, second. So we're going to have wins over losses, which will be 7 over 4. Now, there's two other ways of representing this. You can also represent it like this. You might have seen this before. Wins to losses. Or we can write it either way is valid. These all mean the same thing. There are 7 wins to 4 losses. Questions about that? So just as a point of notation, if you did losses to wins, well, now losses will be on top, wins will be on bottom. 4 over 7. 4:7. Or 4:7. So questions about that? All right. So in the same way we can reduce rates, we can also reduce ratios. So since I'm working with pens, let's say we have this. So we have 64 black pens, 24 red pens. We want the ratio of black pens to red pens. So same idea. We have black pens to red pens. So that means 64 will go on top of 24. So number of black pens, number of red pens. Now we want to reduce this. So to reduce this, we want to find a number that divides in the 24 and also divides in the 64. And these divisions don't have a remainder. Now, to be honest, you actually can have a remainder when you're dealing with ratios and if you're dealing in rates. That actually is okay. In fact, I can do an example with that. So let's say we can reduce this. We can divide top and bottom by 8. And so we'll get 8 to 3. So we could do something like that. So questions about that. And again, it's this idea, if you've ever, with reducing fractions, and we haven't had a chance to talk about this, but the idea of reducing fractions is sometimes the reduced fraction. Well, it represents really the same quantity as the original fraction. It's just this might be easier to visualize than something like this. And something even easier to visualize, let's try to represent this as a unit ratio. So this is something with fractions that we don't do, but it's something you do see with rates, you do see with ratios. We're going to allow numbers with decimal points to be in the top or in the bottom. Now in this case, we want the bottom, just like with rates, we want the bottom to be 1. So there's 1, but 8, divide 8 by 3, doesn't go evenly. 2.6 repeating. Now, you can represent this as a mixed number. And I don't think they ask you to do this in this homework. This is what I'm going to show you is a little bit above and beyond. But you can call this 2 2/3. You can do that as well. But you can have unit ratios. So it's about 2 2/3 black pins to 1 red pin. And that's how we can represent that. Questions about that? All right. So let me do one more. Now this is an example from the text. And this is example number 5 on page 513. But it works like this. And it's just a little trick in here that we're going to do, something to keep in mind. So let's say on average, let's see. Say on average, someone watches 21 hours of TV per week. Let's see. Let me see what they're asking here. So find the ratio of hours of TV watched to the hours in a week. Now, what they're going to do in this problem, so on average, someone watches 21 hours of TV per week. Find the ratio of hours of TV watched to hours in a week. So when we usually think of time in a week, 1 week equals 7 days. So we want to convert this from days into hours. So we take 7 days times 24 hours for 1 day. Again, we're doing that conversion. We're going to make sure that we have the same units of time. So these cancel, these cancel. So time in top, time in the bottom, that means those cancel. And so what we end up getting, if we multiply across 7 times 24, let's see, 140 plus 28, 168 hours over 1, or 168 hours. I'm just going to circle this. It's a sort of preliminary thing. So we've got 168 hours. Now, someone is watching 21 hours of TV per week. So to compare hours of TV to hours in a week, there's the TV hours, and there's the week hours. And what we can try to do here, we can try to reduce this. So what's something that can divide into 21 and say divide into 168? And you can think about this. Well, if you add up the digits here, you're going to get 15. And that means 15 is divisible by 3. So that means this is divisible by 3. It's a little math trick you can use. If you add up the digits of a number and they add up to something divisible by 3, then that is also divisible by 3, that number, the original one. So we can divide top and bottom by 3. Let's see, 168 divided by 3. 56. And then 56 is divisible by 7, so we can divide top and bottom by 7. And so we get 1 hour of television for every 8 hours in a week. One to 8, or with the 2 spelled out. But for every 8 hours in a week, someone's watching an hour of television. Questions about that? All right. So the last thing to mention in this section is proportions. Now, this is an equation. Now, this is an equation where we're equating, setting equal to, 2 rates or 2 ratios. And it looks something like this. So this could be a rate over or ratio, A over B. And we're going to set it equal to something else that could be a rate or ratio. So we have some special names for these. A and D, and let me just double check here. I want to get this right. Yeah, that's going to be. These are called the means. Then B and C, these are called the extremes. There we go. Now there's a special trick we can use for solving, or ultimately solving for one of these means or one of these extremes, and that's what's going to happen in these problems. One of these will be missing. So we can do this. The trick's going to be cross multiplication, or the product of means equals the product of extremes. So in other words, A times D equals B times C. So something to keep in mind when we're dealing with algebra, again, when we have something like two variables, and that's what these really are, they're variables. Granted, they're letters, but we pretend that they're numbers. They're just numbers we haven't chosen yet. But we're still going to treat them like they're numbers nonetheless. So when you have two variables next to each other, in algebra that means they're multiplied together. So this is A times D, this is B times C. So let me do an example. Of how we solve for one of these missing means or extremes. So let's say we have this. What they want us to do is solve for x. So what we're going to do, we'll take the product of our means. Oh dear, let me see, did I mislabel those? Hold on 1 second. So labels aren't that important, but still like to get that correct. Oh yeah, I did mislabel those, I'm sorry. Let me do this one more time. So in your notes, when you have this, these are the means. These are the extremes. So check your notes on that. Sorry about that. In your notes, these are the means, these are the extremes. Just give you a second to change your notes there. All right. So let's go back to this one. So this one, I want the product of the means equal to the product of the extremes. That means 3 times 40, and then 8 times x. Or 120 is 8x. Now what we're going to do here, we're going to go back to what we looked at in section 9.1. We want to get x by itself. Right now the scale is balanced with 8x on one side and 120 on the other. And we assume this is true. So we want to get x by itself to see what balances just plain x. So for multiplying, remember the opposite of multiplying is dividing, just like the opposite of dividing is multiplying. And then for addition and subtraction, they're opposites too. You want to undo subtraction, do it in addition. You want to undo addition, do a subtraction. So we're multiplying by 8. We better divide by 8. So let's see, 120 divided by 8. What's that going to be? It should be 15. Just double check my math here real quick. 4, yeah. And so that's going to be our answer. Questions about that? Let me do one more. Interesting. Say 7.5. So again, we could do means and extremes. So we have our means. Write that again. There's our means. And here's the extremes. So for the extremes, 60 times 7.5. For the means, y times 15. Let's see now, 60 times 7.5, 450. And then again, we'll do the opposite of multiplication, we'll divide. And so we get 30 is equal to y. And that's going to be our answer. Let me do one more. Let me see. So let's say we have something like this. Let's do a story problem. Now, let's say we're talking about dosages, and this is something that comes up if you're going into, say, nursing, if you're going into EMS. This is a big deal. You'll have dosages based on somebody's weight. So and there's a trick they use, I think, at least in your basic EMT class, where there's a way of coming up with these very quickly. But let's say we have something like this. Let's say we have a medication. It's 2 ounces. For every 50 pounds. So for every 50 pounds that a person weighs, they need 2 ounces of this medication for it to be effective. So the question is, how much medication is needed for someone who's 175 pounds? So what we want to do here, we want to look for consistencies. So we have 2 ounces for every 50 pounds. So 2 ounces of medication for 50 pounds of body weight. So we can start out with this. So there's medicine over body weight. And the idea here is, since we're having medicine and body weight, granted they're both weights, but this is medicine, this is how much a person weighs, so it's really, we're dealing with a rate here. So amount of medicine, amount of body weight. We're going to want the same rate on either side. So what this means is that the rate we're going to write here, unless it's exactly the same as this better reduce to that. So we have the body weight, 175 pounds, and well, the problem is they didn't tell us how much medication. So we're just going to call this X. So we don't know the amount of medication. So what we're going to do is means and extremes. So this means we have our means. Well, if we take our extremes, we'll have 20 ounces times 175 pounds equal to 50 pounds. And it's some unknown amount of ounces, X ounces. Now we can drop the units here if we want. We can just call this 20 times 175 is 50x. But we don't want to forget X is going to be ounces of medication. Let's see, 175 times 20 is going to be 3,500. So now we just have to divide both sides by 50. And so we get 70. I just want to remember it's going to be 70 ounces. Oh, wait, hold on. Wait, did I do something? Something's a little off. Oh, shoot, it's 2 ounces. I'm sorry. There we go. Let me run through that again. I think I might have, let me see, did I write that as 20? I might have written that incorrectly. Let me do that one more time. Sorry about that. I think what happened is I had lunch before class, and that's giving me a little bit of food coma, so I'm missing a few things. Better be careful of that next time. So let me do that again. We have 2 ounces for 50 pounds. We have X, 175 pounds. So we're going to get 2, I'll leave the units off, times 175 equals 50 times X. This is 350 50x. Divide both sides by 50. And sure enough, we get 7. And this is 7 ounces. You don't want to forget that. 7 ounces of medication. Whew. All right, there you go. Questions about that? All right. So that's it for this section. That's 9.2, ratios and rates. Chapter 9 is kind of an interesting collection of things. We're going to get into percents in the next section. And percents are pretty interesting. I guess that's another way. A percent is a kind of fraction. So you're dealing with a fraction that has a denominator of 100. So it's another way of comparison. It's a sort of a sub-feature of fractions. But we'll get to that on Thursday. So if you have any questions, let me know. Other than that, have a wonderful afternoon.